Hi guys, once again we do this problem. I read the question first. I start. Figure shows a SFG, that is signal flow graph of control system. Using Mason gain formula, determine the transfer function of the system. So the guys, we begin once again with what we are calling the forward path gain. For the forward path gain, guys, it's just a path from the source of the signal up to the sink or the destination of the signal. That path forward without transversing any node twice is what we call forward path gain. And the first forward path is actually this from here to here straight. We have G1, that's what I have written, G1, G2, G1, G2, G3, G4. Another path we have is the signal can move through this path. So we have G1, G5, G3, G4 is the same. G1, G3, G5, G4. Of course, G5 should be here, but the arrangement doesn't matter. Coming out to loop gains, for those who are the forward path gains, the loop gains, we have a number of loops. Loop 1 is G1, G2, H1. G1, G2, H1, that is one of the loop. Another loop is G2, G3, H2. G2, G3, H2, that is another loop. Another loop G1, G2, G3. G1, G2, G3, G4, H3. And then we also have another loop that goes through G5. And this is now the loop we are talking about. The loops, these are the loops gain. From there, guys, we come to the path determinant. For the path determinant, we have the delta. This is the determinant of the SFG diagram. First, we have the delta, which is 1 minus summation of all loop gains plus summation of all non-tangent loop gains, that is taken 2 at a time, and this one is taken 3 at a time, non-tangent loop gains. So for us, as you can see, we don't have any non-tangent loops. As you can see, all the loops are interconnected. What we are saying, guys, is that if I move through this loop, I will be able, or the signal will still come into contact with another signal that is going through this loop, or through this loop, or through this loop. So all these loops are actually tangent loops. And so therefore we don't have any non-tangent loops. And so guys, we shall just use this equation, this first equation up to that point. And that's what I have done here. 1, delta is equals to 1 minus the non-tangent loops, the loop gains we have talked about. Then we have this delta k, which is that is the loop of that is calculated with the kth path removed. So guys, if we remove one of the path, like this P1, guys, as you can see, all the paths will be affected, all the loops will be affected. In other words, we will not have any loops. If I come and lab this, you'll find that the loops will be disconnected. Not even one will be there. And that's why I've written here, guys, delta 1 is equals to 1 minus 0. Even when you go to the other route, still path 2, we shall have 1 minus 0. And so from there now, guys, we come to what we call the Mason's gain formula. Mason's gain formula is used to find the transfer function, which is TF equals to 1 over delta, the determinant, summation of, that is k equals to 1, that is path 1 up to the kth path. For us, we only have 2 paths. So this one will be P1. Delta 1, we said it's 1. Delta 2 is also 1. P1, of course, we have it as G1, G2, G3, G4. And P2 is G1, G3, G5, G4. Then all over 1 minus the loop gains. Because these loops, all of them had a negative, and here we had a negative, so they become now plus. And so thank you guys for listening to me. See you in another video. Bye.